Continuing on with our discussion, there's several ways to determine the Ka and K or Kb value of a weak acid or weak base. One approach is to measure the pH of a solution prepared by dissolving a known amount of the weak base or acid. And in these problems, given a pH or given some information that can be used to find the initial concentration of the acid and base, you can then calculate Ka and Kb. And there's a few examples there that are in your text for that. Example 1412 gives you the Ka for a weak acid, and the example 1413 gives you the same thing for a weak base. Now, the other thing you can do is you can look at the percent ionization. For this particular equation right here, where you've got a weak acid, the percent ionization of the weak acid is defined by the percent ionization equals the hydronium ion equivalent divided by the HA concentration times 100. You then calculate the ionization percent from the previous problem, and when you see that the pH value is given there as 10 to the minus 2.09. And so that means that it's 0.0081 molar. So from that number divided by the 0.125, you find out that it is 6.5% ionization. And you can do the same exact type of thing with the percent ionization for the weak bases. I'm not going to go into that now. You can also calculate the pH of a weak acid or weak base solution, and essentially what you're doing is you are taking that same Ka or Kb value, giving some initial concentration, and then using those to then calculate the concentration of either the hydronium ion or the hydroxide ion. Once you have either one of those, you just take the logarithm of those to get the pH or the pOH. One thing I should have mentioned is that in Appendix B of the text, it explains the use of these logarithms, how you can easily go back and forth between the concentration and the pH or pOH on these using that information. Now, let's talk about the molecular structure and the acid strength. There are some acids that are stronger than other acids, and we know that Bronson-Lowry acids are proton donors. So consider a binary compound, H plus A, where the strength of the acid depends on how easily the bond between the hydrogen and the nonmetal A is broken. Acid strength increases as bond strength decreases. So here's, again, going back, utilizing your periodic table that you always keep handy, right? This is a periodic property. Going down a group, in other words, going down from top to bottom, the acid strength is going to increase. And the reason for that is because the orbitals of different sizes form the strong bonds. You've got good orbital overlap. Orbitals of different size form weak bonds. You've got poor overlap. Hydrogen is the smallest element. Atoms get larger going down that group. So the HA bond weakens as the A changes going down that group, and the acid strength increases. Likewise, the periodic property of a nonmetal A. You go across a period from left to right, the acid strength increases. The more polar the bond, the easier for a hydrogen ion to be produced. And this is all based upon that table that we had before on electronegativity, because electronegativity increases as you go across that period. So the HA bond becomes more polar as A changes across the period. So the HA bond weakens across the period. That means the acid strength increases. Anything that decreases the strength of that bond will increase the strength of the acid. For example, in this particular one, HNO2, and this is the same ice type of table. But you'll notice that there is no information included for the H2O portion for that table. That's because pure liquids as well as solids do not have input into the equilibrium constant that you calculate. And this gives you the values that you have for that. This particular one right here shows the strength and trends of binary acids and bases. Going across the individual rows, you are increasing your acid strength. Going the other way, from right to left, you're increasing your base strength. Going down from the top to the lower one, you increase your acid strength. And going from the lower part to the upper part in a given column, you are increasing your base strength. Now, sometimes compounds are going to contain an oxygen and one or more hydroxyl group. These compounds can be acidic, basic, or amphiprotic, depending upon the electronegativity of the element E. The electronegativity of E is low, then the bond is polar or ionic. When that happens, the hydroxide ion is readily released and the compound is basic. Metals have low electronegativity. Metal hydroxides tend to be basic. That's the sodium hydroxide, potassium hydroxide, magnesium hydroxide. All of those are quite basic compounds. When the electronegativity of E is high, then the bond A is covalent. The electrons in bond B are pulled towards C. For example, when you have C, a carbon atom, replacing that C there, that COH, that's an alcohol. That's a covalent bond. It's going to be polar, it's going to be weak. The hydrogen ion is readily released and that becomes acidic. Nonmetals have high electronegativity. So here are some examples where you have the oxidation number of the central atom increasing. You've got the sulfurous acid and the sulfuric acid. You've got nitrous acid and nitric acid. And you can see that as you get more electron withdrawing groups from those, in other words, nitrogen goes from +3 to +5, nitric acid is much stronger than nitrous acid. Likewise, from the sulfurous to the sulfuric acid, you're going from +4 to +6. Again, it's much easier to get rid of the OH bonds there. Compounds containing oxygen in one or more hydroxyl group, when they're as intermediate, when the molecule is usually amphiprotic. In the presence of a strong acid, the compound acts like a base. In the presence of a strong base, the compound acts like an acid. Compounds containing oxygen in one or more hydroxyl group, that is the metalloids or elements near the metalloids, have intermediate electronegativity. Examples: aluminum hydroxide. You have a base form and you have an acid form. Now let's talk about salts. A neutral solution contains equal concentrations of the hydronium and hydroxide ion. The reaction between an acid and base is called an acid-base neutralization reactions. What are always the products of such a reaction? You're going to end up with a salt and you're going to end up with water. So this resulting solution is not necessarily neutral, even when the stoichiometrically equivalent quantities of acid and base are used. The nature of the salt form determines whether the salt is acidic, basic, or neutral. So there's four basic types of acid-base neutralizations. You have a strong acid, strong base, and a neutral solution is formed. A strong acid, weak base, and a weakly acidic solution forms. Weakly weak acid and a strong base, and you've got a weakly basic solution forms. With a weak acid, weak base, it's neither acid nor basic. It could be either one. Okay? So, for example, strong acid, strong base. You've got, for example, hydrochloric acid and sodium hydroxide forms sodium chloride and water. The salt that's formed is NaCl, and you end up with an acidic solution. If you have a strong acid and weak base, here you've got HCl and ammonium chloride. The resulting salt is ammonium chloride. And here you end up with something that is weakly acidic. If you have a weak acid and a strong base, such as this case where you have essentially acetic acid and sodium hydroxide, you end up with sodium acetate and water. And this is a weakly basic solution. And for this one right here, this is probably going to, where you have acetic acid and ammonium hydroxide, and you end up with ammonium acetate, you are probably, it's going to be a little on the acidic side. Now here, then what you do is you are going through some different examples here. This right here is the ammonium benzene material reacting with water to form this amine plus the hydronium ion. And this, you go through the different examples there in your book to calculate exactly what those would end up being. The other one that I want to look at is the aluminum ion itself reacts with water. And you can see how hydrated it becomes. That's the H2O. When it's by itself, that means that the aluminum atom has 6 water molecules surrounding it. Okay? The aluminum ion has 6 water molecules surrounding it. And therefore, it can, when as that hydrated form, it essentially becomes a weak acid. And this gives you the type of table that you can use for calculating those sorts of things. You'll notice they don't have the column and this one for the water, because they all understand, and you know by now, that water does not have a contribution to the K factor. Let's talk about the polyprotic acids. Acids that contain one ionizable hydrogen are called monoprotic. Acids that contain more than one ionizable hydrogen atom are called polyprotic. Polyprotic acids ionize in steps. The acid equilibrium constant becomes smaller with each successive step. So essentially, another way of looking at this is you can call them diprotic and triprotic acids. An example of a diprotic acid would be sulfuric acid, and an example of the triprotic acid would be phosphoric acid. Now, this next one, there are many hydrogens in here, but the only one that contributes to it is the one that's way out over here with the bonded to the OH. This is the only one that is going to form this hydronium ion. Okay? So just because there are these other hydrogens in there does not mean that they're going to dissociate. These are all covalently bonded. And I think we'll call it the end for this particular session.